saw a very simple example of non-displaceability on S2. So there, using very elementary techniques, we were able to say that in order for a loop in S2 to be non-displaceable, it has to divide S2 into 2 equal areas. But if you are to move beyond that, you need more sophisticated techniques. And there is a fairly technical, like a very technical theorem of Fukaya and collaborators, which tells you which of the fibers of the moment map have non-trivial Floer homology and hence are non-displaceable. So in order to state that theorem, I need to write down the moment polytope in terms of these inequalities. So that's what I do in the first point. So if X is a symplectic toric manifold with a moment map, so then the moment map can be captured by these equalities. So these are linear equalities, and each of these, inequality I meant. So this is the inequality I'm talking about. And each such inequality corresponds to a facet. So I have capital N number of facets, and corresponding to every facet, I have this kind of affine inequality. And I recall from yesterday, we were working with this Novikov ring, which is just a ring of polynomials, infinite polynomials, and Q is a formal variable. And this was used to keep track of the energies of the curves which we were counting. So the exponent of Q was the energy of some curve. Okay, so this is the key part. So given a moment polytope, I can define a potential that looks like this. So we'll do this for one or two examples to make sense of it. So at this point, I just point out that for every lambda, there is a potential. So I'm essentially defining a family of potentials. And there will be a term corresponding to every facet of the moment polytope. And what the theorem of Fukaya says is that if for a certain lambda, W lambda has a critical point, then that's a Floer non-trivial Lagrangian, or in other words, that Lagrangian is non-displaceable. Okay, let me write this down here because we will use it in the next slide. So the moment polytope is lambda in dual of the Lie algebra such that Li lambda is greater than equal to 0. Li lambda is lambda times Vi minus Ci, and Vi is an element of the Lie algebra, and the potential sorry? Ci, that's just a constant. So that tells you how much your facet is shifted. This facet line is not passing through the origin. So that's why you have a Ci. Okay, so if we were to write out everything in the case of S1 action on P1, what we have is the facets. So in this case, in this example, So in this example, the moment polytope is just an interval. So the facets, we have two facets. These are the two facets. And for any lambda, I write down this potential. For both of those facets, I get a term. And in some sense, the q lambda and q1 minus lambda are measuring the energy of the disks which are incident to that facet. So we will make this point clearer later on. But this is a particularly simple example. So if your Lagrangian is one of the latitudes, and so you have one disk on top and one disk on the bottom, and so these exponents here would just measure the areas of those two disks. So so in order for this to have a critical, so notice this is a function in beta. So in order for this to have a critical point, the q terms should have the same exponent. So if that is satisfied, then it will have a critical point. So so this ties in with what we saw yesterday, that the only Floer non-trivial Lagrangian is the one which divides the S2 into halves of equal area. Okay, so the next example is that of P2. Sorry, say it louder.
No, this theorem you're saying it's only if this has a critical point, then it's non-displaceable.
Yeah, it gives us Lagrangians which are Floer non-trivial. So there might be Lagrangians which are displaceable. Which are non-displaceable but don't have non-trivial Floer homology. That's not what it's about. Okay. So the next example is P2, and we already have the moment polytope drawn in front of us. So this is a moment polytope. So it has three facets, and the inequalities are these three inequalities. Lambda 1 is greater than equal to 0, lambda 2 is greater than equal to 0, and 1 minus lambda 1 minus lambda 2 is greater than equal to 0. So when you write down the potential, you get these three terms, and it proceeds in a very similar way to the previous example. You get a critical point exactly when all the q terms have the same exponent, which happens in the case when lambda is 1/3, 1/3. So basically, in some sense, it's the centroid of this, or whatever, some notion of taking center. But so the idea is that the disks which intersect, so if you will have one disk which intersects this divisor, one disk which intersects this divisor, and one which intersects that divisor, and all of them have equal area. And in some sense, they balance out each other and they don't let the Lagrangian move. Any questions so far? Yes. Exactly. Yes. So in this polytope, if you take any interior point, the inverse image is a torus. It's a single orbit. So yeah, so the non-displaceable Lagrangian is a torus. Yeah. Okay, so now I get into some technical part which we did yesterday to kind of explain how, to just make sense of this magical theorem almost. So I actually made a big mistake yesterday. He was asking me about the curved part, so it was, somehow I was in a hurry in the end, I just said something stupid. So I will fix that now. So this slide is essentially a repeat from yesterday. So, so we saw that, so these mu n's, these are the products in the A infinity algebra of the Lagrangian, and we saw that so mu1 is your differential operator and it does not square to 0 because the A infinity relation gives us this, and here mu0 terms are actually counting accounts of disks, so which are bounded by the Lagrangian. So because we have a non-zero mu0s, we don't always have mu1 square equals 0. And the second point says that the mu0 is called the curvature of the A infinity algebra, and the A infinity algebra is flat if mu0 is 0, and if it is flat, then we have the differential squares to 0, and we can indeed define the Floer cohomology. So another nice property that sometimes A infinity algebras have is the presence of a strict unit, and these are the properties which a strict unit satisfies. And here's where I made the mistake. So what I really wanted to say is this: if the mu0 is a multiple of the unit, then the cohomology can be defined. Because if you, yes, so if mu0 is a multiple of EA, then using the identity for energy, we see that this term cancels out with this term, and you're just left with the differential squaring to 0. So this is the condition for unobstructedness. And let me just give some geometric sense of what this unit is. So in some nice cases, you can define a unit, and the unit will be, so I'm putting CFL here because that's the Floer complex. So your ECFL is so remember that this guy was generated by the critical points. So we defined the Morse function on the Lagrangian, and this guy was generated by the critical points. So in some nice cases, the identity point is going to be the maximum value of the Morse function. And why this works out nicely, I say a few words. So recall that mu n is what do I call it? L max, okay. L max. So is a count of 3 disks, holomorphic 3 disks with n inputs, and the prescribed input is L max. So if this were the ith input, at the ith place, this is a gradient flow line coming in from L max, and we have our output here. So we are trying to count these things, and remember that this is the maximum. So you don't have to do much to lie in the unstable manifold of the maximum, right? The unstable locus of the maximum is open in L. Therefore, if we just forget that point and consider what's remaining, what happens is that the expected dimension of these configurations goes down by 1, because we had a freedom, one-dimensional freedom in choosing this point on the boundary, but we didn't lose anything in the constraint that it lie in the unstable locus of L max. So we lose 1 dimension, and if we have done all our perturbations right, we are not supposed to get those disks at all. So that means that most of the time we just get a 0 over there. And the only time when you don't get a 0 is if everything's just a constant. So basically, this whole configuration is a constant at a certain critical point, and you just have this L max point coming in from there. So that corresponds to the first equation. So if anything is non-constant, by forgetting this trajectory, you're going to get a 0. But in general, when you say something about forgetting, that becomes a complicated thing to impose when we are doing perturbations. So, okay. So that's broadly where this unit comes from. And in the second line, I'm saying that in order for it to be unobstructed, I also, so remember this point. We will talk about this a little bit in the torus case later on. Yeah, so basically we are saying that all the disks with a single outgoing edge, in the torus case, the only place these can land in is the maximum. So that is the condition, which I'll come back to later. Okay, so so clearly we see that these disks are quite important in what we are doing. So we are going to be talking about this in toric manifolds for a little bit. So before I get into that, so I wanted to make one more point, that the potential is also essentially a count of disks. So the potential is essentially terms in mu0, but they are grouped according to the brane structure. So this is something I've not talked about at all. So when you are describing, when you are defining your moduli spaces, I said at some point that for the sake of orientation, you need to choose a spin structure on the Lagrangian, but you also additionally need something called a brane structure, which I'm not talking about. So for different choices of brane structure, you will get different moduli spaces, and the sums we were writing yesterday were summing over all brane structures. So so the W lambda separates these according to the brane structure, and the mu naught just takes it all together. So these two are essentially very similar. You can get one from the other. So since everything is about disks with one outgoing edge, let's look at that a little more carefully. Okay, so a property of the toric manifold which we'll be exploiting is that they themselves are a symplectic quotient of Cn. So I just define what I'm saying. Basically, I'm not giving the proof. So what is a symplectic quotient? So we defined a Hamiltonian space, with a torus action. And if for some value of the moment map, if the T acts freely on the fiber, I can quotient. So sorry, one thing to remember, this is not a toric manifold. So I'm just talking about a general Hamiltonian action of a torus. This, what I'm saying is T need not be half-dimensional. T is smaller than half-dimensional in general. So if T acts freely on any of these fibers, then I can quotient out that level set by the fiber, and that's called a symplectic quotient. So for some people who have not seen this before, when you're taking quotients in symplectic geometry, you cannot just quotient out by a group, because you will no longer have a symplectic structure on the quotient. So you need to do this two-step process. One step is restricting to a level set, and the second step is quotienting by a group. So essentially you cut down your dimension by even dimensions, and you also make sure that this space actually gets a well-defined symplectic form. And a small observation is that this, in case, since if X is in addition a projective variety, we can also write this quotient as a complex quotient. So XS will be a Zariski open set in X, and TC is the complexification of the torus. So this can be realized in a complex geometric way. Okay, so an example to keep in mind is the simplest example. So Cpn minus 1, as we saw, is a toric manifold. By toric manifold, I mean something that has action of a half-dimensional torus. So we saw the case of Cp2, but Cpn minus 1 is the same thing. So, and that can indeed be realized as the quotient of Cn by S1 action. So S1 acts on, any element of S1 acts on Cn in the standard diagonal way, and the moment map is the sum of the moment maps of the individual actions. And so if you restrict to a level set, you get S2n minus 1, and quotienting out by S1 will give you a CPn minus 1. So in general,
it has to be a regular value.
yes, so yeah, only 0 is not a regular value. Any positive number, yeah, I should have said greater than 0. Yeah, that's a mistake. So in general, if you have a symplectic toric manifold whose moment polytope has n faces, then we can realize X as a symplectic quotient of Cn by some torus. Yeah, so they, and it actually fits in, so let me just read out this thing. So if we consider the action of the full torus, S1 to the n on C to the n, so the result is that there is a subtorus of this torus called G, such that X is the symplectic quotient by G, and so we are left with the quotient acting on the symplectic quotient, which is X, and that is precisely the T action on X. And this is it's a fairly simple result. Okay, so now why this is nice for us is because we have lifted our setup to Cn. Because remember that not only is a symplectic quotient, it can also be thought of as this complex quotient. So we can study disks in Cn, which is much easier. Yes.
Quotient of Cn.
Right.
Or some G.
Yes. Yeah. Okay. So if you have done this part, so and then now you look at your Lagrangian in your symplectic toric manifold, and you lift it. So it will lift to a Lagrangian in some level set in Cn. And so what you get by lifting is going to be a Lagrangian submanifold of Cn, and it is a product of circles in Cn. So it's a capital N dimensional torus in Cn. So now our problem is, what are the disks in Cn whose boundary is this product of disks? And this is what follows is essentially just complex analysis, which says that a holomorphic disk in Cn with boundary in the product of disks L lambda tilde is given by a Blaschke product. So, so if you have a disk in Cn, you can just break it down into components, and in every component you get a disk whose boundary is on a circle. So those are, so we are essentially looking at holomorphic maps from a disk to disk, so which is given precisely by this Blaschke product. So basically for every n, for each of these components, we'll have, for the jth component, we'll have dj is kind of the degree of this Blaschke product. Okay, so U tilde has n components, as capital N components, because it's a map to Cn.
Oh, you're saying the.
Yeah, yes, these are just the components of U tilde. Okay, so now now let's come down to X. So X was a quotient of Cn. So X is equipped, so there's a natural complex structure on, a standard complex structure on X because it's a quotient of Cn, a quotient by a complex group. So, so then any disk lifts to a disk of this form. So essentially we have a classification of these disks, and if this is your lift, the index, so in Gromov-Witten theory, you would have seen that the Chern class plays a role in defining the Fredholm index of a curve, right? So similarly, when you have curves with boundaries, the parallel quantity to look for is the Maslow index. And if this were your lift, the Maslow index is just twice the sum of these DJs. So, and in the toric setting, disks are very well behaved. Firstly, they are completely classified by this result of Cho and O. So I guess this is what I was explaining earlier is actually part of Cho and O's paper. And they further also say that all these holomorphic disks with respect to the standard almost complex structure are also regular. So no perturbations are required. So yeah, the theorem ends here. I should have started a new line there. Okay, so now we come back to our setting. We were interested in disks with a single outgoing edge. This is what I had drawn on the board earlier. Asymptotic to some critical point in L0. Let me draw it. So this is what we are interested in. So this is a disk, and this is a gradient flow line mapping to some critical point in L. And we want to, so we want to see under what conditions will I get zero-dimensional moduli spaces. So the formula for dimension is dimension of L plus Maslow index of U plus these other terms. One is comes from point here. It has one-dimensional freedom. And -3 is the automorphisms of the disk, which we saw yesterday, and minus codimension of L0. So we want this number to be 0, and so this number, in order, so that there is not, we don't have much choices because these two quantities are quite large. So in order to reach 0, the only possibility is if the codimension of the stable locus, the stable manifold is dimension of L, which essentially means that L0 is the maximum value. So if the codimension is the total dimension, that means it's just a point. And it's a stable locus is a point means L0 is the maximum value. And index has to be 2. So if you set these values, you see that the dimension there vanishes. So when you are counting the potential, ideally, only the index 2 disks are getting counted. And if there are spheres of negative Chern class, they may throw you off, because what will happen is you have a disk, say with a positive Maslow index, you have a very negative sphere, and when you put the sphere on and glue it, then you get a disk with, that will contribute negatively to the disk. And then, so then if this number becomes small, then you no longer are able to enforce this condition that the codimension has to be dimension L. So you end up getting configurations which are incident to other critical points also, which is bad. So you lose unobstructedness because of the presence of negative spheres. So if you are working in a toric manifold which does not have negative spheres, you just get unobstructedness for free. Okay, so if there are no negative spheres, then mu naught is precisely this guy, and L max is the identity in your A infinity algebra. So all the contributions to the potential are from Maslov 2 disks, and the picture in the P2 case is what we had already drawn earlier. So remember that if the Maslov index is 2, there's exactly one of these which is not 1. So only one, only one component will be non-constant, and that too will have exactly a single place where it intersects a divisor. So Maslov 2 disk will have a single intersection with one of the toric divisors. So this needs a little bit of thought, like you need to play around with the correspondence, but it's not too hard to see. And in the P2 case, we had drawn these disks. So what really drawn here, so this is a disk which will be a unique disk which is incident on this divisor. Because the moduli space has dimension 0, there's only one disk. And so for each of these divisors, there is one single disk which is getting added on in the potential. Okay, this is. So we have our mu 0 and a potential which we said that it's essentially kind of writing the mu 0 in a different way. Now you might wonder, if you recall, what was the FOOO theorem? The Foucault's theorem said that, where is Foucault's theorem? Yes. So Foucault's theorem says that W lambda has to have a critical point. So you might wonder where, so we want to set the derivative of the potential to 0. So you might wonder how the derivative of mu naught enters the picture. And that is actually, yeah, I think this is somewhat complicated. So if this is, you're seeing this for the first time especially. So basically there's something called a divisor equation in Gromov-Witten theory. So in Gromov-Witten theory, what the divisor equation says that if one of your marked points is constrained to lie on a codimension 2 submanifold, then what you can do is, how do I say this? You can essentially just forget it, because any sphere is going to intersect a codimension 2 submanifold, and you count the rest of compute a small Gromov-Witten invariant, and then count the number of multiplicities. So you can do a similar thing in the Foucault algebra case. So suppose if one of your inputs, so I'm just considering a single input now. So let me consider mu1, which means I'm counting disks with a single incoming edge coming from a critical point of index 1. So just to be clear, since I've not quite defined what my convention of index is, what this means is that the unstable locus has codimension 1. So if that is the case, any disk you consider is going to intersect the unstable locus, especially if B is a co-cycle. So it's actually not a single critical point, it will be a sum of the critical points. Then any disk will intersect your unstable locus. So what I can do is I just drop this criteria altogether and instead just simply count mu naught. Right, so let me explain this. Sorry, there is a mistake here. This is not B comma L naught, this is just L naught. And there should be an L naught here. I was just making it this morning, so yeah, so what this is saying is that you drop the condition that it has to be incident on the unstable locus. Instead, just count this with a single outgoing edge and you multiply with this number. So for every u, that number is going to be different. But the reason things work out very nicely is because this term is precisely the derivative of this term. So you end up getting a derivative of mu naught. So if the derivative of mu naught is 0, then mu1b is 0. So if you start with the cocycle, an ordinary cocycle in the Morse case, in the Morse sense, you actually get a cocycle for your Fukaya algebra. And so that's how we end up with a derivative in our picture. So basically, if you kind of put all these pieces together, you will be able to prove the Fukaya's theorem in the case where there are no negative spheres. But if there are negative spheres, we need fairly complicated perturbations, which I am not talking about here. So moving back to examples, which are fun. So one more example I consider. So this is. So far we talked about CP2. So now this example is about a blow up of CP2 at a point. So let me just spend 1 or 2 minutes talking about what blow ups are. So blowing up a point on a symplectic manifold. So let me just consider Cn, and I'll blow up the origin in Cn. So if you have seen blow up in algebraic geometry, you know exactly what this is. So when you're doing it in symplectic geometry, the only additional thing you need to do is prescribe the form on your exceptional divisor. And so you need an extra parameter to prescribe what your blow up is. And let's call that parameter epsilon. So then this blow up is given by deleting an open epsilon ball centered at the origin, and then modding out the boundary. So this is modding out by the S1 action on the boundary of the deleted ball. So this the boundary of this ball is S2n minus 1, and when you mod out by S1, you get a CPn minus 1, which is your exceptional divisor. And it's quite remarkable that when you do this construction, you get a smooth symplectic manifold, because it doesn't look very smooth, but it turns out that it's actually smooth. And further, this construction also goes very well with toric geometry. So if you blow up the vertex of a moment polytope, then let's just do the example of CP2. So we recall that the CP2 had this moment polytope, and this point corresponded to 0, 0, 1. So now, suppose I blow up at 0, 0, 1 by an epsilon amount. Everything I'm doing is I can do it in the torus invariant way, so that I continue to have a torus action on the blow up, and then the moment polytope is going to look like. So basically, here I deleted a ball, and that's like chopping off at the tip of a small neighborhood of the vertex. And this quantity will be epsilon. Okay, so if you have this moment polytope, then it has four inequalities which determine the polytope. 3 of them are same as the CP2 inequalities. Lambda 1 and lambda 2 are non-negative, and lambda 1 plus lambda 2 is less than or equal to 1. And the third one is the new one, which says that lambda 2 is less than or equal to 1 minus epsilon. The potential is as follows. So you see that in the potential, the first 3 terms are terms we saw in the CP2 case, so we get one new term. And so we get a new non-displaceable Lagrangian which was not there in CP2, namely we get a Lagrangian here. So the 1/3 was there in the previous case also. And we get one more Lagrangian which is close to the exceptional divisor. And the way to, so this one will have 3 small disks which are incident to those 3 divisors. So then it does not have any disk which is incident to the 4th divisor. But these 3 disks have the same area. And somehow, so this is interesting because if you have a small blow up, you produce a Floer non-trivial Lagrangian, and it does not matter what's happening in the rest of the manifold. So yes, you are right. Actually, this is a mistake. Yep. So the reason we get a critical point is because it's some an implicit function theorem. So if you have the small q exponent in 3 of the terms and it produces a non-degenerate critical point, you can adjust the big term. So it's it's a version of implicit function theorem which helps you find this critical point, and and basically, even if you don't have CP2, if you just blow up a point in any 4 manifold, or for that matter in any higher dimensional symplectic manifold, you're going to produce a Lagrangian. But to say that it needs, so this is actually a result which is proved in this paper by Charlest and Woodward. And what they do in the paper is they say that, so let me just read out the theorem. So if you have a manifold which is a symplectic sum of 2 manifolds in both M1 and M2. So just let me draw a silly picture. M1, M2, and X is a divisor in both, and then you've taken symplectic sum along X. And there is a Lagrangian in M1, and it's a Floer non-trivial Lagrangian, so it has some disks which help you minimize, produce a critical point. So you have L is a Floer non-trivial, it's not non-displaceable, I should say Floer non-trivial Lagrangian with none of the minimum disks incident on X. So X is sufficiently far away. So in this picture, you know, I could have just broken it here and put in some other manifold, for example, and I would still have that as a Floer non-trivial Lagrangian. With none of the incident disks on the separating divisor, then displaceable on M. So again, here this P is required to be toric Fano, but yeah. I mean, it can be removed, and I don't know. So this, another point I want to make is that this Lagrangian is also kind of interesting in that the Floer non-triviality of this is not disturbed by this blow up. So the same result can, in some cases, the same result can also be applied to say that if you do a faraway blow up with the disk don't see, then can actually say that this Lagrangian is not disturbed. And okay, finally, working on a project to find Floer non-trivial Lagrangians on M0 n bar. So here, I recall that using a construction of Kapranov, M0 n bar can be realized as an iterative blow up of projective space Pn minus 3. So when I say a suitable symplectic form, whenever I do blow ups, I have to decide what is the symplectic form I'm taking on the exceptional divisor. So if I make sure that the blow ups are all small, then I can, in some sense, find all the Floer non-trivial Lagrangians. And the reason I say all of them is because they'll actually generate the Fukaya category. So that's all I had to say. So if you have any questions.
Blow up is at the other.
Okay, here. Then I produce one more Lagrangian here. Yeah, but if I make the blow up bigger and bigger, then this analysis doesn't.
But that should also follow from that lambda it will be more.
Yes, I'll get one more term. And yeah, and if there, then it will have disks which are incident on those three devices.
Like a blowing up here means it's like correction from that already has a non-displaceable for us. Might be a naive Invariant.
Yeah, it's yeah.
Each one has this. I'm just saying it might be a naive Invariant geometry way of looking at it, but blow up you're just connecting some with CP2 bar.
Yes, yes.
That has a copy of a non-displaceable torus.
Right, right.
Is it that torus that's showing up here or something else?
I'm not sure. Yeah, because there are many torus, right? We are kind of making a choice. Yeah, but if you can kind of transfer your computation to that CP n minus 1, I'm not sure.